All right, springs. Okay, we have a railroad. Oh, this one's not a spring. We have a railroad car with a mass and some kinetic energy. It gains that much energy and increases its speed from something to something else. Okay, so let's figure out how much kinetic energy it started with. So we started with like some kinetic energy and we added some amount and then we have our new total. And they want to know the final speed. Okay, so kinetic energy is 1/2 mass times velocity squared. And they're telling us the change in kinetic energy is 1.98 times 10 to the 6. So that's 1/2 times the mass. The mass doesn't change. But we can do final minus initial squared. Let's do this. So 1.98 times 10 to the 6 equals 1/2. The mass is 10,000. The final, we don't know, but the initial is 7.61, and that is squared. Okay, that's tiny. Okay, so first I'm going to write it over here. 1.98 times 10 to the 6. Half of 10,000 is 5,000 times VF minus 7.6 squared. That all looks yucky, so I'm going to take care of that last. So first I'm going to type in 1.98 E6 divided by 5,000, and I get 396 equals VF minus 7.6 squared. So I'm going to square root both sides to get rid of that squared. So the square root of 396 equals VF minus 7.6. Now without that squared, I get 19.8997 equals VF minus 7.6. So I'm going to add 7.6 to both sides and get 27.5 meters per second equals our new velocity. And we're going to think it through and say we gained energy, so we should be faster than 7.61. So yeah, that is my final answer. Number this one. The formula for spring potential energy. Some classes say potential spring energy like this. Some say elastic potential energy like this. Either way, the formula is 1/2 kx squared. That k is the spring constant. And that's in newtons per meter. And that x is the distance from equilibrium. And that's in meters. So these springs, they have a position they like to hang out at. That's called equilibrium. You can squish them and give them energy, and that distance is the x. Or you can stretch them, and that distance is also the x. Because whether you're, I'm looking around like I have a spring. Whether you like squish it, and it's going to fight against you, want to push back. Or if you stretch it, it's going to fight against you and want to snap back. It always wants to go back to equilibrium. So the distance from equilibrium, that's significant. Okay, so the energy is 1/2 kx squared. Again, that's k is the spring constant. That's like a property of the spring. How stiff is it? It's not the capital K for kinetic energy. That's a totally different thing. So be careful with your k's. So we're going to say 1/2. This 756, that's our k. And the x, it needs to be in meters. Oh, and ours is in meters. That's so nice of them. So 0.05 squared. So I'm going to say 0.5 times 756 times 0.05 times 0.05. And I got 0.945 joules. That's the way.